Ich werde den Vortrag auf Englisch machen. Ich glaube, das war auch auf die Webseite geschrieben. Ihr dürft alle auf Deutsch also Fragen stellen. Ich mache auf Englisch, weil ich fühle mich ein bisschen gemütlicher. Und es ist einfacher für mich, das auf Englisch zu erzählen. Ja, danke Matthias für die Einladung. Kurz über mir, also ich bin Goran Piskachev, ich komme jetzt aus Paderborn. Ich bin da schon 8 Jahre, habe da studiert, Master abgeschlossen und ich arbeite jetzt als wissenschaftlicher Mitarbeiter bei Fraunhofer Institut. Ja, da machen wir Industrie- und Forschungsprojekte, ein bisschen zwischen Industrie und Forschung. Wir versuchen, die Forschungsergebnisse in Industrie zu bringen. Ja, und dazu mache ich, also bin ein Promotionsstudent an der Uni Paderborn, wo ich versuche, die statische Code-Analyse-Tools besser zu verstehen und die Konfiguration von diesen Tools ein bisschen zu automatisieren. Also wie man kann diese Tools besser anpassen auf ein konkretes Projekt. Ja, und welche sind die Probleme, die Entwickler haben, diese Tools zu nutzen. Yeah, for this talk, I will talk about a bit on this topic. So, what do we mean by configuring those tools, and what are the problems there, and what are the research, state-of-the-art research. Yeah. Okay, so I guess at least you have heard of some of those tools. Here is a collection of some known industry tools, commercial tools, but also some open source tools. And I know that some tools like are mandatory to be used. In some companies, it's a choice of developers to decide if they want to use such tools. So there are different processes. The idea is that we can use such tools to help during programming, finding as many security problems as possible early, rather than having the tools running afterwards in the build, in the CI, and having tons of issues to fix at once. So to cluster a bit, those are here like more open source tools. Yeah, I guess, did you ever at least heard of any of those? Yeah? The rest, no? I see some people. Okay, so maybe you should have a look. At least those are for free, yeah? At least you can have a look what they can do and how they can help you. Some of those tools offer you plugins that you can install either in Eclipse or in IntelliJ or Visual Studio Code. Yeah. So what we are researching, or there are some studies that try to answer questions why developers want to use those tools, why they don't want to use these tools. So there are issues, of course, with those tools. And as you see here, it's a kind of screenshot of a regular size project in one of the tools, Fortify. And usually you really see those numbers here, right? And when you come in the morning after the build process is finished, you have 4,000 critical.
It all seems to work.
The question is, where do you start? Yeah. So there are studies and to see why are the problems like that, but many of those are actually false positives. So when you really see the code as a developer and you understand what is going on, it's not really an issue. So you just close it. Yeah, and often there are this one study which at least in the research is often used to motivate these issues, that often there are many of those checks are turned on automatically. You as a developer don't know how to configure this, how to turn them on or adapt the rules to really work for your code base. We also did some kind of small studies. At least last year I was working on 2 projects. In one project we did interviews with 9 developers, because the study from the previous slide was a few years older, so we wanted to check if some things are improving. At least those that I interviewed, all of them have used static analysis tools, and here are some of the comments they said. Like, it's kind of challenging to use the big configuration files of the tools, and many of them even said like they don't even want to try to write rules because they don't understand how to do that. It's kind of task for security experts or people who really understand static analysis. Then we also did an online survey where we collected more than 350 answers from developers from Germany. It was part of a bigger research project, AppSecure. It's funded by the North Rhine-Westphalia state. And there were 2 interesting questions for me, so I chose them here. You see that still there are people who don't really use security check, tools for security checks. Like 150, but also like half people are like using static analysis tools. Yeah. So one way of using static analysis tools is to try to find security issues, but of course there are other applications. So let's go a bit more into code and some examples. In the next part, I'll try to explain what do we mean by taint-style vulnerabilities, because many of the security vulnerabilities on code level can be formalized as a taint problem, and I would like to explain you what does it mean, because if you understand that, you as a developer can really know better how this different kind of vulnerability work, so it would be easier for you to configure such tools. Here is some code in Java. I think, yeah, there are some issues in this code. Probably you see at least one. Yes? Sorry, yeah, yeah. That's a very typical. So usually we always use it in motivation examples. It's easy to understand. The idea is from how we can detect such problems statically. This means we don't want to execute the code. And how usually static analysis tools work, they implement a taint analysis. And taint analysis will actually try to start to track data, relevant data in your program. You're interested probably in the entry points where data is coming from outside. In this case, we have a request, and the value coming from the parameter is something we don't trust, and we want to track where it's going. And in SQL injection, if we do a data flow analysis or taint analysis, in this case, we will track the value through the code and where it propagates. We will see that it comes to this execute query. This is so-called typical sink in taint analysis. The get parameter is so-called typical source. And in taint analysis, we want to try to find a way if there is a path between source and a sink. And yeah, actually, if we see here, we have kind of a encode for SQL method, which let's assume this was a good sanitization. Probably in Java, you would use more likely prepare statement. But for some scenarios, you can have some kind of other libraries that would make the value safe here to be executed. And such analysis tools should also be aware of those sanitizers that you use. So in this case, a good analysis should not report this as a problem, right? Otherwise, it's a false positive for you. Something else, if we look in the code, actually in the value of user ID, it's then propagated to this URL. And it reaches a send redirect here, which is actually also kind of a sink method. And it's just a different type of vulnerability. It's so-called open redirect, right? So in the same code, we have the same source, but we have 2 different sinks, 2 different kind of security problems. So those things the analysis, as I said, is kind of a general concept, taint analysis, but how you really configure those sources, sinks, sanitizers is then for what kind of security issue you can apply the analysis. Yeah, feel free to stop me if you have any questions.
This is all Java-based, which has the advantage that the static code analysis can work on the bytecode, which is nicely abstract for them to look for sources and things. Is there much work on other languages?
Yeah, so my research and my expertise is more into Java because we use the Java bytecode directly. We transform the bytecode usually into so-called intermediate representation. And then these intermediate representations usually are really simpler. They have like 15 operations around. So it's much more easier to write your data flow analysis rules on really only 50 operations rather than the bytecode, which has, I don't know, 200 or something operations. So yeah, in other languages there exist also, of course, tools. Usually, for example, in C++, there are many approaches that base on LLVM. So they can use LLVM as an intermediate representation. I think in Java, it's really the most tooling is well established. For C, C++, there are tools now more developed. But like languages like JavaScript, I don't really know that you really analyze this statically. I think in industry it's mostly dynamic, so testing, fuzzing. There are research approaches for JavaScript, like dynamic languages. There are publications, but I think it's not really applied so far. Yeah.
Pretty well covered.
Yeah. Okay. Very good.
Only 60% was negative. So.
Yeah, probably.
which is not much for JavaScript.
Yeah. I know that also SAML have support for JavaScript. You can do some kind of type checks. Rules, but it's usually for if you have a dynamic languages, you have to really model your frameworks, and if you have your frameworks already modeled, then you can have some kind of analysis there which can work in your scenario. And usually probably those tools already have models for the well-known frameworks, right? If you apply it to a really specific framework which is not so known, I don't think they will really work. Yeah, okay, so my research, as I said, is more like Java world, so, but of course I'm interested in the other languages as well, and I think in Java is the most advanced state at the moment. Okay, so how, as I said, I introduced what we mean by sources, sinks, sanitizers, what we usually have in static code analysis. We have our code base that we want to analyze, and we have those tools there, and what they really need is those kind of lists of sources, sinks, and sanitizers. Most of the tools have like manually selected typical methods from security experts usually. This is quite expensive task to do, and in this talk I'll present a way of how we could automate this with using machine learning. This is something we were working in the last 2 years, and last year presented 2 papers. We also presented it at HISA DevSec conference. So this approach, we call it SWAN. It's kind of a supervised machine learning. So that's really the core, what we do there, but we also implemented a tool so-called SWAN Assist that you can use to create your own security relevant methods. So the idea is you as a developer can provide some examples of your code base for the machine learning algorithms, and then you can improve those lists because we are using so-called active machine learning. This is the general idea, and I will explain in the next part of the talk how this works at the moment, what we did, and how good it is. Yeah. And in the last part of the talk, I will talk a little bit on the languages that you can use to specify rules for the analysis. Okay, so as I said, how we can automatically detect such methods from your code bases and always adapt your code base to specific problems, and you can use those results then in the tools. As I said, we published this work last year, so this is more like scientific work. If you're interested, you can read. I'll try to explain it today much more on an abstract level, not going too much into scientific results. I think the audience is more like from industry coming. Am I correct?
Yes.
Yeah? Okay. Yeah. So as I said, first I'll try to explain how the SWAN works, so the machine learning part, and how machine learning can actually help us in security. So usually we follow some kind of very typical steps in machine learning when you want to apply it. Let's say we need to define kind of a problem. We want to find a specific data that will fit the models that we will create. Then we need to create those models, so-called classifiers in this example. And then we can test and validate how this works. So the problem is for us, let's say we have a code base in Java and we want to see what are the methods in our code base that are typical sources, sink sanitizer for specific vulnerabilities. And that's what we call by vulnerability specific SRMs. Then we need to collect good training data because this is a classification problem. So we need training data and then we need testing data. Testing data will be any code base that we have or Java library that we want to analyze or the entire project that you work on. Then we need to create such classifiers. This means we need to provide kind of so-called features. Features describe the data. In this problem, single point data is a single method. Okay. And then as I said, we can do some tests and validations. Usually in machine learning, people do 10 cross-fault validation. That means you have already labeled data and you can run it several times. You do different subset of the data and then you compare how well it's working. So whether really a result labeled with source is really a source or not. So that's how you can calculate precision. Also recall. So this is the big picture of how this works. Actually, we have a training data. We have features that describe this data. In SWAN, we manually selected it's a small set, only 230 methods. But for the classifiers we created, this actually already gave some good results. When you create training data, this is a bit you need to make sure that the data is balanced, that you have enough examples of like positive examples, negative examples for specific feature. And then we would get the results. We also did some testing, what type of algorithms work best there. The implementation, what we did is we used Veka. It's just Java library that you can use and implements many different algorithms. We kind of tested several of them and we chose the one that gave best results for specific tests that we did. Yeah, so in SWAN we have 25 types of features. This is something we designed. And I would like to explain you what do we mean by feature here. So as I said, a data point in the training set is a single method. And let's say we have this get parameter method. We have the signature and we have the implementation here. And what we really have as features are, for example, name-based features. We check for specific keywords in the package name or method name and so on. Let's say typical sources would have like get, sync will be like, I don't know, write or send, or there are typical keywords that we identified to describe this data. Yeah, so name based on the method names. Then we also check on the types. So like it's very often that sources will have some kind of return value and things will probably be void. Then we also have some kind of features that we really check for the data flow here in the implementation. We use a static code analysis framework to analyze each method on its own, so just intra-procedural analysis. So there we check, for example, if a value from a parameter would flow to a return value. So these are kind of patterns that tell us if a method could be source, a sink, a sanitizer, and so on. Then we also check like modifiers. So these are some examples of or kind of features that we implemented. And the tool we implemented, so SWAN has like so-called 2 rounds of classifications. We have actually for each of these boxes here a single classifier. This means we take the code base as an input. This is our testing data set. And we run it and try to classify each method as a source or not source, sink or not sink. So these are boolean, right? So there are only two outcomes, right? So in this case, we can have methods that would be at the same time source and the same time sink because it's a different classifier. Once we run this round, this is so-called very general. We allow that we do a lot of false, the precision. We made it so that we really get a very broad number of methods in the first round, and what we do, we actually created new classifier for specific vulnerabilities. I use just here the notations of CVE, common weakness enumeration. For example, we have implementation for 7 of them. That means the code base that you can take, you can run this tool, you will get lists of methods. It will generate for you typical sources, for example, for SQL injection, typical sinks for some of those authentication problems. So we have several vulnerabilities that we selected.
So your training set, you've already analyzed for those CVs?
Yes. So in the training set, we have, as I said, 230 methods some around. We already have examples of all of those. Yeah, all the methods in this are already labeled manually by us for specific classes. In this case, classes are the sources, sink, sanitizers, authentication method, and also the classes are the CVEs. So this is what you can do automatically, and this is a fully automatic process. If you want to use it, it's also open source. You can have a look. The training data is also open source on GitHub. Here is some things we did to see how good it is. First, we looked into related work in the literature. There were already some similar approaches. For example, the first one, SUSI, is also kind of machine learning approach. And they already, it was applied for Android only framework, and the features they use, we also reuse some of them because they were already really good. We just extended new feature types and tried to make it more Java general, so not only a feature specific to Android framework. There was also then extension of that, and we kind of compared against those two that we found. We ran it the same. We took the same version of Android that was used in SUSI, and we ran all 3 approaches. And then, because the number of methods are really high, we selected randomly 50 methods for sources and sinks, and we only do this here, sources and sinks, because those 2 approaches can only classify sources and sinks. So they don't really do vulnerability-specific categorization, or they don't do sanitizers. So that was what we could compare. And we could, based on this experiment, we could go slightly better in the precision. Okay. Next thing we did was,
And how good was the classification for SWAN finding sanitizers?
So here we cannot compare that because I will show in the next. We did also like, yeah, in the next, after this slide, it will come this, okay? So this is just an overview, the number of methods that all these three different approaches found. So if you see, SWAN is very general and finds a lot of methods as a sources, as I said, because that was our goal, because we do a second filtering with the CVEs at the end. And SUSE, for example, is really only focused on data leaks, not other types of vulnerabilities. Yeah, so then what we wanted to see how really precise is SWAN. We ran SWAN on 12 different Java libraries. And then again, from each class and each category and each framework, we selected again 50 methods. We went through them manually, classified them, more than 3,800 methods. And the average weight was, for all of them, was 0.76. Yeah? This was the precision over all. Here are also sanitizers, here are also sinks. In the paper, we have the categories separately. So for sanitizers, we have different value. For source, here is just averaged.
So one would be perfect.
Yeah, one would mean we are 100% correct. Yeah. What we also realize is when we only do the first round, we have much better precision. And when we start, we look only the precision of the CVE, we are really dropping there, which means 6 or 6.5 methods out of 10 are correct. The rest are not correct. And that was the motivation to actually see how we can improve this. And that was where SWAN Assist comes. The idea is that we can improve really much those results if we get more data examples in the training set from your code base. That's what we mean by adapting the learning, by giving a few examples. Yeah, so on the next few part, I will explain you a bit on SWAN Assist, so what it is, how you can use it. This is just small motivation. So generally, there are already approaches where in checkmark you can label some of the findings as a developer, and checkmarks needs to learn that next time should be better and don't show you specific problems. Even though I also asked in the interviews people who use checkmarks, they also say it's mostly like kind of filtering, it's not really learning. But the idea is already there that you as developer can give some feedback and the tool will be improved. There is also some scientific work on this kind of idea. This was also initially like a related work. So the idea is here, we use SWAN again, and we introduce the developer or the user here. Currently, I would say security experts can do such things because they understand what are very good typical sources things. They could create typical list of methods that, for example, in one team you have specific third-party libraries that you usually use, and you have a list for those libraries. And if you have some examples of those libraries in your team, then you can improve this for the list, and then those can be reused as in a team, right? We also implemented suggest an algorithm called SWAN Suggester, which will tell you what are the methods that you should probably label, because they will really influence the classifiers. They will make big changes in the classifiers. And it's an IntelliJ plugin that you can use. The idea is you can see always your data or your lists on this side. They are labeled different kind of sources things in the code base. You can directly see here what this is source. This is an authentication method labeled. You can reclassify then each method. And this manual reclassification, it will be saved, and then you can rerun the learning. Next time you will get different results. This is also open source. If you're familiar with IntelliJ, you can use it as a plugin, or at least have a look. Then what we try to see how fast we can, or how much effort we really need to put into usually in a, let's say, one project that we selected, how much effort we need to add in order to see how much we can improve the precision, right? So what we did, we manually, again, took a smaller application of 1,600 methods. We manually labeled them. And we tried to answer the question, how much methods we need to add and to get increase in the precision. And we did 2 rounds. Once we use our algorithm for suggesting methods, and once we randomly picked methods and add them. So the idea was we started with the initial training set of 230 methods that we had in SWAN. And in each run, we add 2 methods. We add 2 methods because we always take care that you have a positive example and a negative example for a specific feature that we chose at the moment. So in each run, we select a specific feature, and we choose 2 methods. And what you see when we take 2 methods of the testing data and we put them in the training data. So this means that at the end, all 1,600 methods and somehow will be added in the test training data. And we always measure the precision, because as I said, we manually already labeled the methods, so we can calculate precision there. What we see is that using this algorithm, the suggester, we will in the beginning much faster improve the precision rather than randomly doing this. And if you see, for example, if we want to reach like 80% of precision for such project, we would need to add around about 60 methods. Yeah, so we start with not so good precision, under 0.78, and after 31 runs, this means each run is 2 methods, this is 62 methods, we will reach at least 80% precision. Any questions here? Okay. So this is an experiment we did on one project, one application. Yeah.
One thing that surprised me is that in real-world applications, all the sources and sinks are somewhere in the framework, because you don't actually talk to the browser yourself. It goes through a framework serverlet API and stuff like that. Or with SQL, there's just one JDBC, and in effect, the source of the sink is only in one place, which then has a few things that may call it, or wrappers, and etc. What surprised me that you have so many methods that you're labeling as sources and sinks, because in effect, there are actually only very few.
There are many, yes, but these are for, as I said, in the first round. Usually the number of methods when we classify in the CVEs, we have published those numbers also in the paper. Usually you come around 20-30 methods in application for, let's say, a SQL injection, right? When those numbers here that you saw, they are really big. Here, let's say, this is the whole Android framework. They are like 30,000 methods. So from 30,000 methods, SWAN found that the blue number, so it's 12,000 methods, would be kind of sources, which is very much, right? But if you run then the CVEs, then the second this drops, like I think in Android it was like 100 maybe, right? It really drops, and this is something that you can use. This first round, it's something, if you give it to a tool, it will explode. It will probably not finish.
Interesting, did you analyze what features actually tend to correspond to what methods, as in what's the strongest indicator for a resource, that it's a public method or?
We did one at a time analysis for feature. We ranked, like what we did, we also reported in the paper, we turned off one feature and see how the results change, and then we could see at least a single feature how influence, and we also have a ranking of the features. I don't know if that's the best way to do it. Probably there are more, I'm not very machine learning expert there. Probably they will use some more complicated kind of analysis for relevance of features, I think.
And what was the outcome? Was there anything that stands out that was exciting?
So for the CVEs at least, it was always that the naming features were the most important. As I said, there are features that are based on the names or the keywords that you use. Average number of feature instances, actually, we have 25 types of feature, but for each classifier you need to instantiate them. And usually here we use about 40 to 60 features, instances in each classifier, and here we have around 20. And usually those 20 are always name-based, and they are really already giving you the results for CVE, but not all CVEs can be really formalized in this way.
So if the method's called unsafe user data, then it's flagged up as...
Yeah. Yeah. Okay, so I'll move to the last part. I wanted to talk a little bit now on domain-specific languages for configuring static analysis tools. This is something like recently we are working, and I'm interested in this. I was looking into different languages that different tools provide. Checkmark has its own language, SAML has its own language, and so on. And I think from my feedback that I had with the studies we did, developers don't really use them. Usually only experts are using such languages. And what I want in my research is actually to design a language that would be much more easier for developers first to understand, and use it in a simpler way so that they can write their own kind of checks and adapt the tools in a specific way. This is an example in SAMLQL, how it's even not the full, I really reduced. There was also like 50 lines of code more, how you specify a SQL injection rule, and actually they have a queries. It's in this part here, from where select, kind of a SQL-like language. The language is very powerful. You have a control of the whole code base. You can define everything you like. You can import different kind of languages, so they have like support for different kind of languages. They model already a lot of frameworks that you can use, and you can specify different properties. And here the language is a bit declarative, so I think that's also something for many developers is not very easy. You have in the front part you declare some kind of objects that you can use. You can create your own classes, so it's also object-oriented way of writing code. But you really need to understand that there is a graph structure of your code and nodes, and they really need to understand how taint analysis would work, so that you can configure such things and write your own versions. They also have a typical kind of classes that would model you different kind of remote so-called remote flow source. These are like in typical frameworks, they will match specific method calls, like remote calls. That means this is a very typical source for that, and from there you would like to start tracking. They also have like typical sinks and in the where part you usually create kind of predicates, so this is called to a predicate, or you give some constraints. And then you, in select part, you want to tell what really the tool should return as a result. So yeah, how do you find this language? Any thoughts of this?
It's a lot like a scripting language that is declarative.
Yeah. Yeah, so this is one example. This is the language of check marks. It's a bit more like C#. They did it. I think it's a bit more understandable. Here is just example in the language how you could use this find by position call. If you see, you have kind of for here. It's more like imperative. Yeah, this is just another example for you. There is a different one in CogniCrypt. This is an open source tool which was also developed in our group, and it's kind of a joint work of more research institutes. The idea of the tool is that you can check for whether you correctly use encryption libraries like JCA. If you really corrected the if you use the library in a correct way, like if you use the right algorithms with the right padding, with the right key size, and it's checking such things. And this is the language they have. What you do is actually for each class that you want to check, you need to create such specification. You can create some kind of objects, then you can model events, like here is an example for get instance. Then you model the init sign for private key, then you can have like constraints. You can say that the algorithm value here needs to be in either one of those values to be secure. Then you can have some kind of ordering that you have to have a get instance call, then you need to have initialize code and update one or more, and then sign. And then you also have this requires and ensure, which is kind of a predicates, but I think it's also not very easy to use this language as a developer. As I said, it's more likely for experts. And this is something that I was working. So I tried to design a taint analysis language where it's a Java syntax. And here is an example of how you can create a query in a language. What you would need is declare methods that you want to reference from your code base. Here is an example of, like, we want to model execute query to be, we use such calls out and in. Out is usually for sources because we want to get to track the data after, so the data coming out of this method call. And in is for following the data coming into a specific method, because here what we want to say is per parameter 0, which is the first one, is the value we want to track. And for here, for the sync, it's for example the value here also that we want to track. This is the actual sync. This is just an example. For the sanitizers, we will have both, because usually is data that we are checking flowing into the sanitizer and then getting out of the sanitizer as a save value. This is how you can model that. And the thing is that this can be generated using SWAN. So the methods that SWAN can generate it in this format. You can choose. And you would have this in separate files. And you would do this once, and then you could reference such methods in your queries. And the queries would say here, I have a query which is of type taint flow object, and we use fluent interface in a way of specifying. We will say from M1, if there is a flow from M1 not going through sanitizer, but reaching to M2, this means reaching the sink, then I want to report a message. yeah, we could also, the language supports also like more complicated things. You could have here and or. You can have kind of parallel flows that you can express. You can also have through here. That would mean that the data flow has to go through specific methods, so some bad thing to happen. Okay, so recently we also did a small user study with 21 participants. We invited developers, and what we did is we tried to evaluate the usability of this language. We did kind of a small introduction where we explained them what the SQL injection is and how taint analysis works. And then we did a comparison between this language that I showed you last and the language from SAML. And the way was that we did small tutorial with them, and then we gave them a task in 10 minutes to write a specific query on their own. What we measured here is how many participants actually wrote a correct query, like only that it was on syntax correct. In fluenTOL, the language, 15 out of 21 were able, in SAML 14. We also measured in what time they did it. So usually in fluenTOL it took less time for them to specify a rule. And then we also asked them at the end of the study also this system usability scale, where you ask different 10 questions for each of the languages. And then you can calculate some metrics on usability. And yeah, this is something that is work in progress now. It's not published, but yeah, we are planning to publish it this year and also make the language open source. At the moment it's not. We have also an analysis that works with this language. Okay. I think I will summarize. Yeah. Any questions so far? Okay, let's summarize. So in this talk I explained you on some parts of how we can configure static analysis tools. One of the topics was how we can detect automatically typical sources in sanitizers. We used machine learning to help this. So you can do fully automatically with SWAN, or you could use SWAN to semi-automatically create such methods for tools. And then we also showed in the last part different types of domain-specific language, how the rules for those tools are specified, and for that you can use to specify different vulnerability problems. Okay, thank you very much.